Cloud networks are massive, redundant, and constantly shifting. When something breaks, it rarely fails in isolation. Instead, you get a cascade of correlated signals, hardware glitches, control plane hiccups, routing flaps, all firing at once. Traditional rule-based automation chokes on this complexity. It can't scale, it can't adapt to topology, and it leaves engineers guessing. So how do you actually find the root cause? The answer isn't more rules. It's causal reasoning. Today, we're breaking down a production-grade framework that uses graph-based causal discovery and time-aware probabilistic inference to solve root cause analysis at hyperscale. The first hurdle is dimensionality. A single cloud provider monitors millions of devices across thousands of signal types. Running exhaustive causal discovery over that space is computationally impossible. The team solved this by introducing two structural constraints, an automation ontology and spatiotemporal grouping. The ontology maps raw metrics, traces, and logs into a standardized hierarchy of concepts: observations, risks, faults, and actions. They defined 14 fault categories, 11 action categories, and organized the network into 185 logical layers. That gives them roughly 4,800 binary variables. But even that is too big to test pairwise. So they group signals spatiotemporally. When an incident escalates, they only pull faults, risks, and actions within a configurable number of network hops and a time window. This creates an incident context, collapses redundant variables, and drastically shrinks the search space to only what actually co-occurred during that specific failure. With a manageable variable set, the real causal graph construction begins. The data is binary. Each variable is either 1 or 0, depending on whether an event fired at a given minute. To find directional relationships between these binary time series, they use bivariate Granger causality, but adapted for discrete event data. Instead of linear regression, they fit logistic regression models. For any pair of variables, A and B, they test whether B Granger causes A by comparing two models. The restricted model predicts A using only its own past. The unrestricted model adds B's past as a predictor. They extract the log likelihoods and degrees of freedom from both, then compute a likelihood ratio statistic. Under the null hypothesis, this statistic follows a chi-square distribution. If the p-value drops below a threshold, typically 0.05, they retain the edge. This filters out spurious correlations and keeps only statistically significant directional links. But pairwise tests inevitably create indirect paths. If C causes B and B causes A, the pairwise test will flag C to A as well. To prune these, they run conditional independence tests on variable triplets. For an ancestor B of target A, they search for a third variable C that precedes B. They test whether C is conditionally independent of a given B's past. If it is, the link from C to A is removed, leaving only C to B and B to A. This triplet analysis reconstructs the true mediation structure. They allow bidirectional edges to account for timing jitter and missing signals, and they accept that the resulting graph may contain cycles. In practice, it's a causal summary graph, not a strict directed acyclic graph, but it's sufficient for downstream inference. Discovery is only half the battle. You still need to rank candidates when an incident hits. Here, S where the time-aware probabilistic inference comes in. For every edge in the graph, they compute a conditional probability function over time lags. Specifically, the probability of occurring given B occurred at lag delta t, they discretize time into 1-minute bins, and estimate this probability over a 20-minute horizon using historical incident data. The result is a curve that shows how likely A is to fire after B at each minute. Some relationships, like control plane errors leading to link issues, peak around 6 to 10 minutes. Others, like link issues causing packet loss, spike within the first 2 minutes. When a new incident arrives, every signal in the context becomes a candidate root cause. For each candidate, they traverse the causal graph to find all directed paths to the impact variable. Each path gets a likelihood score calculated as the product of the conditional probabilities along its edges, evaluated at the actual time lags between activated variables. If a node on the path wasn't observed, they apply a small constant epsilon to avoid zeroing out the score. The system then takes the maximum path likelihood for each candidate and ranks them. The top 3 candidates above a threshold are returned. This isn't just correlation matching. It's structural and temporal path scoring. On a blind evaluation of 35 labeled high-impact incidents, this method recalled the correct root cause in the top 3 predictions 85.7% of the time, with a 74.3% exact match rate. Compared to rule-based automation from senior engineers, which sat at 48.6% exact matches, and heuristic baselines like first signal or nearest hop selection, the causal approach consistently outperformed. More importantly, this isn't a lab experiment. The system was deployed as an API in production, processing over 800 real incidents over 7 months. Engineers rated the output highly, with nearly half of sampled incidents receiving perfect scores for accuracy and completeness. It's not flawless. The spatial abstraction that made this scalable also compresses too much information. Signals from sibling devices in the same layer get treated as identical, and path-scoped or endpoint-scoped metrics fall through the cracks. Future iterations will need finer-grained spatial modeling, explicit temporal constraints during discovery, and possibly graph neural networks to learn spatiotemporal structure more flexibly. But the core insight holds. Data-driven causal reasoning, grounded in structural constraints and time-lagged probabilistic inference, scales where rules break. Root cause analysis in cloud infrastructure has always been a battle against complexity. Rule-based systems hit a wall because they can't capture dynamic, topology-aware interactions. By combining an automation ontology, spatiotemporal grouping, Granger-based causal discovery, and time-aware path likelihood scoring, this framework turns a massive, noisy signal space into a tractable causal graph. It doesn't just find what's broken. It traces how it broke. And as cloud networks grow more distributed and failure modes more intertwined, causal discovery isn't just a nice-to-have. It's the only path to reliable, automated operations. If you want to see the full methodology, the dataset breakdown, and the mathematical derivations, the paper is linked below. Thanks for watching.